Okay, hi. So in this video, we're going to look at this paper, which is looking at how tube voltage might affect the radiation dose and the image quality in chest radiography. So what they did was they looked at some regions of interest and they measured contrast noise ratio and they measured some radiation dose, entrance surface dose, and they compared 70 kVp tube voltage with 140 kVp tube voltage. So this video looks at a group of second year radiography students having read this paper and having discussed how the experiment could go in previous weeks. This was the session where the paper, the experiment was repeated using ProjectionVR simulator with the help of a tutor who happened to be me on this occasion.
Right. So just to recap, then we've come up with a couple more constants that we wanted to document, which was centering point and collimation. What about patient position? Direct. Projection. Okay, so we can criticize any paper that doesn't have all this information, so that we can, if we're having to guess, then we may get it wrong, won't we? So T7, that's fine. Right, that's good. You all with me?
Yeah.
Good. So next, what we're going to do is we're going to set this down to 70 kV, which is our first exposure. Yep. And now what we've got to do is we've got to expose it to see with a test MAS to see what the exposure index will be. Yeah. Try and get the exposure index as close to 300 as possible. I think it goes there. It's just a test of exposure. So we'll give. Does anybody know a chest X-ray exposure off the top of the head? It's perfectly. I wouldn't expect you to, because of the fact that all the machines are automated. So automated now, aren't they? You literally don't even look at the MAS values that the machine gave. Is that true?
Yeah, pretty much.
Yeah. So so that makes a problem because we can't really guess at this stage. So we're just going to have to expose this to see what. Okay, so that's terrible exposure index, only 23. So we need to go up by a factor of 10 to get to 230, and then we need to go up a third. So if we increase that MAS, remember we're using a very long source image distance. It seems crazy, doesn't it? Let's see what happens. So we've got 231 now, and we need to get to 300. In fact, I'll tell you what we'll do. We'll go. It seems crazy, 250. So we'll change this to 250 as our exposure index we want, and just increase this by a little until we get near to. Okay, so that's our number we got. So with 70 and 56, so 56 MAS. Let's see if I can move that. Let me move that to there. No, I don't want to replace it. Insert column. Perfect. Delete. Okay, so exposure index we achieved was 259. Okay, so this is exposure 03. So I'm going to give this a number. This is number E003. We've got collimation marks on the receptor, so we can measure the size of those in the future. And then we've got tech data tabs. So can you guys make a double check of this? Because when I read the numbers out, can you make a note of them? So we're talking about the first exposure, which actually is exposure 3 because we did a couple of test exposures. 70 kV is the setting that we're testing. We had to give an MAS of 56. The exposure index that we achieved was 259, which is near our constant of 250. So everything is as we expect. So now we need to read the dependent variables out. So the first dependent variable we've got is entrance surface dose. Okay, so the entrance surface dose for that exam, EO3, can you see that is read out at 0.839 milligray? Okay, then the next one we don't know yet because we're going to have to load this image into our Dicom. Let's try.
Is it the one right in the middle or right on the right hand side?
Yeah, well done. There it is, micro Dicom. So this is a free Dicom viewer, which you can download for free on a PC or a Mac, actually. And now what I need to do is find on the desktop Group 1 X-ray Science and Technology. This is you. This is our patient. And this is our third exposure. That's the one we want. Okay, so we've now got the chest X-ray up in micro Dicom. And what we can do here is we can draw a region of interest. And so can I task, I think the idea was that you draw a region of interest. In the paper, they had what they called lesions, they had nodules, didn't they? And they drew a region of interest over a nodule and then a region of interest over the normal lung tissue. So what I think what we should do is draw a region of interest over an area of dark lung and an area but the point is that it has to be reproducible. So for example, we could look at, if I drew a region of interest here, which is, it makes sense if it's a certain number of millimeters size. You see, I'm looking at the area here. 75 millimeters seems reasonable. So Control C, Control V. No, that's not what I want. Delete. I have to pick it. That's the pick button. Pick Control C, Control V. Let me move it? Yeah. Okay, so that's not very good, is it? Right, let's go over here. Let's go to here so we can see them. Right, do you see what I've done there? So I've got a region of interest, a circle, and what it's doing is it's looking at all the pixel values in that circle. Now I know that the PowerPoint, the lecture that I did on quantum mole, that was sort of essential reading for this, because the idea is that each of those pixel values is slightly variable, even if you're X-raying through something that's very thin, very much the same standard. So we're going to have a lot of different pixel numbers in here, but they all approximate to an average, which is for lung tissue, which is obviously a darker black than for rib and lung tissue combined. So what we're looking at is this mean value. So can you write down this number, please, all of you? So the mean pixel value for the background, is 1939. And the standard deviation background is 69. Yep. and the mean value for the object, which is the rib, is 2475, and the standard deviation for the object is 50. Also, can someone please write down the area, or all of you write down the area. So we used a 75 millimeter squared region of interest. Now we need to also, because of reproducibility, we need to say where we put it. So we put it on the right hand 1, 2, 3, 4, 5, 6, 7, 7th. And which bit is that? Is that the posterior or the anterior part of the rib?
The posterior?
Yeah. So can you, so we've put the region of interest on the right 7th posterior rib. Yeah. And we put it in a place where it was in the mid-clavicular line, shall we say? And then we put the region of interest in the, so that's the 6th intercostal space in the mid-clavicular line on the left-hand side. To reproduce that, they could do that because they could find the mid-clavicular line, they could count down to the 6th intercostal space between the two ribs, and they could draw a 75 millimeter square circle and reproduce that. Do you see what we're doing?
Yeah, that makes sense.
Fine. The other thing that we need is we probably need to print. I'm going to press the print screen button because what we want to do is we want to capture this. We might use it as a we might use this as a figure in our poster. You've got to be thinking about how your poster's going to look. So I'll print screen that, and we'll save that. So I'm just going to put that onto Paint, Microsoft Paint, paste that, File, Save As. We'll put that in your group thing here, and we'll call it JPEG. We'll call it measurement CNR measurement ROIs. Save. Okay, that's good. Okay, can someone read me back these numbers? Because what we're going to have to do is we're going to have to create insert column, insert column. I think we can't do this calculation here. So what I'm going to do is I'm just going to put all of the numbers that we've just captured in here as raw data, and then we can do the calculation. So the mean pixel value for the background.
1939.
Perfect. Now, what do we call the background? Which was the background? That was the lung, wasn't it?
Yeah.
We remember. And then we've got mean pixel value obj. Oh, actually, we need standard deviation, don't we? So remember all the trouble we had with that symbol. So we'll copy that rather than go through all that trouble again. So standard deviation background, please.
Was that 69?
Someone
Yeah,
confirm?
69, yeah.
Yeah.
Perfect. That's why we need more. Teamwork makes the dream work. Right. Obj. The object was the rib.
2475.
Yeah.
2475.
Yeah.
And we don't actually need this number, but I couldn't remember which one we needed. But let's put it in anyway. What's the standard deviation of the object?
50.
That
50.
Thank you. Now I'm going to put in here, I know you've done it, but in here the region of interest is 75 millimeters square. and we'll put them. We have put the measurement area, so it's obj is the right 7th posterior rib in mid-clavicular line. Yeah, so that's the object, and the background is the left 6th costal space in mid-clavicular. All that anatomy comes in handy, doesn't it? So a teamwork, a multidisciplinary team doing this sort of research, which includes radiographers, physicists, radiologists, is by far the best. Okay, we need to collect the rest of the data, so we can do that calculation. I mean, it's relatively easy. You use equals m_obj, so equals open brackets m_obj minus m background divided by standard deviation of m background. Okay. Oh, I didn't put a bracket in. Put another bracket in there. Yeah, that's good. So that's a ridiculous number of decimal points. So we'll format that. Format column, number format, and we'll call it 2 decimal places. I think that's probably still too big. We'll just do 1 decimal place. 7.8. So that's our image quality number in objective terms, CNR. Oh, it's exciting. Is it going to go up or down when we do the 105? So that paper, you know, sounds like, I don't know if any of you have felt very intimidated by this sciencey stuff, but, you know, looking at that paper, you probably thought I would never be able to do an experiment like that, publish it, get peer review published, go to a conference, present a poster. Do you see what we've done this in half an hour? We've made our first exposure, and maybe we spent half an hour, we've spent an hour. So we spent an hour last week, an hour the week before, and half an hour so far, and we're already, so 3 hours work, we could have all of the data to write up one of these papers, couldn't we? So does that look less intimidating?
Makes it sound more confusing.
Say that again?
The actual paper itself makes it sound so much more confusing than what it actually is.
Yeah, it does. It's all, but as soon as you start to break it down into things you've seen that you can actually relate to, then it starts to make it easier to read all these papers. Right, so let's go back to our exposure. So now what we need to do, we need to set our next experimental condition, which is 105. So we're going to go, now there is something called the 10 Kvp law, right? Which means every time you put 10 Kvp on, then you halve the MAS. So in this case, we're going up from 10 to 80, from 70 to 80, sorry. That would mean that the MAS would be 25-ish. And then we went from 80 to 90, that would mean the MAS would be about 12-ish. And then if we went from 90 to 100, then the MAS would turn into about 6-ish. Yeah, that's what's called the 10 Kvp law. So we're going to use that as our, so I'm going to go to 105, and I'm going to use the 10 Kvp law to drop this down to about 6 as my first guess. Yeah? So that's my first guess. We're going to hit the expose button. Hey, look at that, guys, 249. Now, I promise you I haven't done that before. Have you heard of the 10 Kvp law before?
No.
There's a paper actually that tests that out. You might find in your travels. It's by Peter Hogg at Salford University in Andrew, England. So So if you, when you're doing your searching, you might find that paper. It's handy it's handy to have these sort of ideas in your head, these theories, which allow you to make changes if you've got patients who, you need something different. Okay, so we've got a new image. Exposure index is 249, which is bang on. So we need to look at the entrance surface dose. So write these down, guys. Teamwork makes the dream work. So the entrance surface dose is 0.266. We need to do the M background. So we open up microdicom again. Okay, so what I'm going to do, I'm hopeful, but not necessarily entirely. Let me pick both of these. Yes, Control C. I'm very hopeful that when I open the next image, I'll be able to paste them onto it in exactly the same location. No, I've done that before. That's brilliant. So, okay, so reading off. So I can't remember which is which, guys. Can you help me out? But the one over the intercostal space is 2014, the mean. And that's 70 as the standard deviation. Is that background? That's background, isn't it? And then the mean object is 2481 with a standard deviation of 48. Okay, so can you tell me what they are back at me, please? So mean background lung.
2014.
And standard deviation background.
70.
And the mean object for the rib.
2481.
And standard deviation for that.
48.
If I drag that down, we should get. Now, in theory, I was going to say in theory it should be lower. The contrast noise ratio should be lower, and it is. So we've dropped, the image quality has dropped slightly in terms of the objective measure of image quality. There's less contrast between the rib and the, it's more grey, less black and white, which is what the theory would suggest. So now we go to 140, but looking at our dependent variable dose, we've dropped the dose from 0.8 to 0.26. So we've massively dropped the dose to the patient. Okay, 140 next. So in theory, when we go to 140, this should be 0.3. Now, the 10 Kvp law does break down at high kV, so it's probably not going to be as accurate this time. But it was proven to be pretty accurate between 70 and 100 kV in the paper that I read. But let's just see what happens. Yeah, so that's very out. Still not worked at all. We've got an exposure index of 33. So we're going to go up to 10 times that. So we're going to go to 3. So now if we expose that, we should get some actually 250. Okay, so 2.5 gets us an exposure index of 265. You see, they didn't have to do this in their paper because they used an automatic exposure control which did this for them, if you see what I mean. That's what an automatic exposure control does. It fiddles with this number to get this number the same, depending on which patient is in the beam. So I'm going to try 2.2 to see if it gets closer to 250. Which which of those is nearest, guys? 233 is 17 away from 250. 265 is 15 away, isn't it? So 265 is closer. So we'll go to 250 then, and we'll expose that. Well, I've already got it, so we don't need to do it again. So this one, 140, exposure 6. I haven't actually written that down in the previous one. So this is exposure 6. And we need to go to microdicom. So we now need to, this one, isn't it? Exposure 6, 141 by 2.5. Open and paste. Fantastic. Right, write these down, guys. So the mean background is 1965 with a standard deviation of 68. And the mean object is 2403 with a standard deviation of 46. So the exposure was 2.5 MAS. The exposure index was 265. The dependent variable milligray for our exposure was 0.201. And the, right, okay, guys, mean background lung?
1965, is it?
Phil, I don't know if I'm looking at the wrong thing here, but that one's the 233, not the 265 that you've got on the screen right now. The one that I can see.
Oh, yes, sorry, yeah. I'm actually reading the number from here, which is the exposure 6, 125.
Right,
But
okay,
you're right,
sorry,
I've still got the
confused
exposure.
myself.
There you go, there's the one we're doing. Perfectly correct, check me. Okay, so the mean background is 1965. You both agree on, you all agree on that?
Yeah.
Standard deviation background?
68.
Okay. Mean object for the bridge?
2403.
And the standard deviation for the object?
46.
So that's 0.4, so the image quality drops a little bit more. I am so pleased that's worked out. So the question now, guys, is that does this, you know, when you read the paper, do our results come up the same as the paper's results? Yeah. So that's what I want you to do this week, is to come up with write your poster. In fact, we could have a go at that. Let's just do a graph. What I'm doing here, guys, is this is how I would do a graph. You might be better at Excel than me, but this is how I would do it. I would copy that, and then I would copy the important independent variable, because you want to graph an independent variable against a dependent variable, yeah? So I would copy those side by side. What you do is you just do that one, and then you insert the graph. So then if we copy the dependent variable dose, copy that one. That's my excuse anyway of why I'm doing this badly. So now we do in fact, it's a lot easier just to copy that down. Okay, so now you've actually got your tables. These are your two tables that you would give to, you'd put in your column. So if you go like that, you center them, text align center, and put a box around them. Maybe put them in bold. There you go. So we've got a table for one dependent variable. We've got a table for the other dependent variable. And we've got a graph for one dependent variable there, which needs a bit of fiddling with. And we're going to just about to do a graph for the other dependent variable, which will need a bit of fiddling with. So I'm going to do this graph as well. Insert graph. Okay, so that one there is image quality, and this one here is dose. So I'll put that down here. Just trying to move it. Control text. Control V. So you've now got the graphs you need, the tables you need, and you've got all the constants you need. You've got a screen grab of the image. Okay, so you need to write a little intro and background, the aim, which the aim is to find out whether tube voltage, affects what. Well, basically, your aim is what is the optimum tube voltage for a chest X-ray. Yeah. Main results. Now this is the way. So you put a table or graph there, a table or graph there, and a table or graph there. So you've got room for. So you could put maybe two tables and one graph, or a table and two graphs and another table. It's up to you. You can fiddle around with this. This is just a suggestion. So you put your results there. Your method. So this is where you talk about the constants and what you altered. Your discussion about what you found, and your conclusion, and then you put any references in there. The thing about a poster, have a look at. You got the link, didn't you, to the posters for the UKIO that I sent you?
Yes, I believe.
So have a browse of those, because that gives you the sort of ideas. You can change the font size so you can get more or less in.
Okay. Yeah.
Be interesting. What you need to do really in your discussion is you need to compare your results to this previous research that you've found. And in your intro and background, you need to point out that other people have done this research. Yeah, so you may only have one or two references, but one of the references will be that paper that you read. Yeah?
Yeah, that makes sense.
Okay, so if your research, if this results have confirmed and given exactly the same results as the other paper, then that's one thing to say in a discussion. If yours are slightly different, that's another thing to say in a discussion. And your conclusion should be telling us what the optimal, because if your aim is what's the optimal KVP, your conclusion should tell us what the optimal KVP is. Or tell us we don't know what the optimal KVP is because the results are inconclusive.